This is Dr. Elliot Hollifield, and this is a video lecture for MAT 1070 covering Chapter 5.1 on inverse functions. Let's first define what we mean by an inverse function. We've talked about several different examples of functions. We've talked about polynomial expressions. For example, something that looks like x squared plus x plus 1. We've talked about the graphs of straight lines, something that looks like, say, 3x plus 2. And we've also talked about rational functions, one polynomial divided by another. How about x squared plus 1 divided by x? Now our goal is to consider inverse functions. We can consider these functions as machines which take this input x and relate that to the output y we get by doing the calculation when we plug in the number x. And so we can draw this picture where here we have the domain. These are all of the x values that we can pick to plug in the function. Then f is a machine which does a calculation with this number and then carries that number to the range, carries it to some y value. It turns out that if this function f satisfies a certain property, if it's 1 to 1, then in fact there exists an inverse function where the inverse function takes this y value and it takes it right back to this x value. So the property is that if we first plug x into f, then we get y. Then if we plug that y back into f inverse, then we go back to x. Therefore, if we compose the two, f inverse composed with f of x equals y, f inverse of y is equal to x, so f inverse composed with f of x is equal to x. It also holds that we can compose in the opposite order. If we start with f, we start over here, f inverse goes to x, and then f carries x back to y. But we'll relabel here and just say x. If we first go from the range to the domain with f inverse, then we can go back from the domain to the range with f. And so this should also be equal to x. Now our goal for the rest of this presentation is to consider each types of function that we've talked about so far in this course and to determine if they have an inverse function, and if they do have an inverse function, then what is it? The fundamental property that we need for a function to be invertible is for it to be 1 to 1. This also means, in simpler words, that it passes the horizontal line test. Imagine we take any horizontal line. There's lots of horizontal lines we could draw, but does this graph intersect any horizontal line that we draw more than one? If it does not intersect any horizontal line more than once, then indeed this is a 1-to-1 function, and therefore this function has an inverse. Here is an example of one which is not 1-to-1. I've drawn a horizontal line which intersects the graph once. So this function is not invertible. Here, any horizontal line only intersects once. This one is 1-to-1, so it has an inverse. Here's a horizontal line. It intersects 1, 2, 3, 4 times, so it's not 1-to-1 and not invertible. Now we have a discrete graph. There's only 1, 2, 3, 4, 5 points. So we can only draw 5 horizontal lines and intersect this graph because it is indeed 1-to-1, and hence we can come up with the inverse function. Now again, here with this example, every horizontal line we can draw can only intersect this graph once. So this is an example of a 1-to-1 function. All of the examples which are 1-to-1 have inverse functions. Now our goal is to determine for those types of expression what is the inverse function. Keep in mind, what is the fundamental property of an inverse function composed with the original function? This has to give us x. So now we're going to do a test to determine whether or not these two functions are inverse functions by doing the composition in both directions. If we get x, when we compose them, then they're inverse functions. If we don't, then they are not inverse functions. So let's try the first example here first. Let's do f of g of x, f of g of x. That is, we do f of 2x minus 3, and that is equal to 2x minus 3 plus 3 divided by 2. Now, minus 3 and positive 3 cancel. We get 2x over x. The 2's cancel, and we indeed get x. Now let's try the other direction. Let's do g of f of x. That is g of x plus 3 over 2. So we do 2 times x plus 3 over 2, and then we subtract 3. Well, the 2's cancel here, and then we have x plus 3 minus 3, and we indeed get x in both directions. So these two functions are inverses of each other. Now let's try this example. F is 3x and g is 3x. So if we do the composition, f of g of x, that's equal to 3 times g of x, which is equal to 3 times 3x, which is equal to 9x. So this one's equal to 9x. It turns out the opposite direction, since they're the same functions, will also be equal to 9x. That is not equal to x, so these are not inverses of each other. Here we have a discrete function. Remember that a function is just a set of ordered pairs, x comma y. So if we call this function f, let's say it only had this one ordered pair, then it passes the horizontal line test, and its inverse is this list, which is given by just by reversing the direction of each of these ordered pairs. So if f is this one ordered pair, then f inverse is this one ordered pair. We would just switch the y for the x. And so we can write down what is g inverse here. We take each of these ordered pairs that occurs in the list and switch them. 8, 1, minus 8, 2, 2, 3, 0, 6, and 3, 8. So now what is g inverse of 2? G inverse takes 2 to 3. We can also come up with what is the inverse function of this line. Here, if y is equal to minus 4x minus 13, then what we need to do is solve this expression for x. So now let's add 13 to both sides. And now let's divide by 4. So if y is equal to minus 4x minus 13, then the x is equal to 4 plus 13 minus 4. That says that the inverse function, h inverse of x, now I'm just doing a relabeling here, that'll be x plus 13 divided by minus 4. So now we have our inverse function. So now let's do the composition. If we have an inverse function and we compose it with the original function, this is a notation to stand for h inverse of h of minus 1. Then this has to give us minus 1. Let's go through the steps and verify this property. First, we would need to do h of 1. H is this line, plug in 1, that gives us -4, -13, or -17. Now we'll plug in -17 to H inverse. -17 plus 13 gives us a -4. Oh, I've caught an error here. I'm supposed to be plugging in -1, and so that'll be +4 -13 for -13, which gives us +9. We should have a +9 here. So let's correct that. Now we plug in +9. That'll be 9 plus 13 gives us -9 here. Plug in -9 here. 13 minus 9 gives us 4. 4 divided by -4 gives us a -1. So indeed, we get what we were expecting. Now let's consider this function, x squared plus 8. Let's first draw a nice picture here. We have this function, x squared plus 8. Looks something like this. And now we want to come up with the inverse function. Since we're only considering this function on the positive side here of the y-axis, this function is indeed one-to-one. If we were to draw the other side in the negative direction, it would not pass the horizontal line test, and hence would not be invertible. But since we've chopped off that negative side, it is invertible, and now our goal is to come up with the inverse. We set y equal to x squared plus 8, and now we solve for x. Let's first subtract 8, is equal to x squared, and then we'll take the square root of both sides, keeping in mind that these are all positive numbers here because we're only working on the positive side. That says that x is equal to the square root of y minus 8. Notice we didn't get a plus or minus here because we're only working with the positive side here. That tells us what the inverse function is. Now we know f inverse of x, we do a relabeling, that's equal to x, the square root of x minus 8. Now, what is the domain of f inverse? Recall this picture. If this was the domain of f, f takes that to the range of f, but then f inverse eats numbers and spits out numbers in the domain of f. The range of f is the domain of f inverse. The domain of f is the range of f inverse. And so if we know what the range of f is, that would be from 0 to positive infinity. And therefore, the domain of f inverse is also the range of f. The domain of f inverse is the same as the range of f, which is from 0 to positive infinity. Now let's try another function here. We have x squared plus 4. Again, we're chopping this off on a certain region so that this function is one-to-one. Now let's find its inverse function. If we set y equal to x plus 4 quantity squared, then we'll take the square root of both sides. Now we can drop these parentheses and subtract by 4. Now we can write the inverse function. F inverse of x is equal to the square root of y minus 4. Now what is the domain and what is the range of f? Once we know the range of f, then we know the domain of f inverse. Let's draw our picture. This is a translation of the function x squared to the left by 4 units. So the vertex will be here at -4, 0. The range is still 0 to positive infinity. And the range of f is the same as the domain of f inverse, which is from 0 to positive infinity. Now let's try a square root function. Similar story. This is a square root function shifted over to the left, be equal to 0 at -5, and then go up looking something like this. So the range of this function f is equal to 0 to positive infinity. Now let's find our inverse function. Set y equal to the square root of 5x plus 25. Square both sides. Y squared is equal to 5x plus 25. Now subtract 25. Y squared minus 25 is equal to 5x. And now divide by 5. That says that x is equal to y squared minus 25 divided by 5. So now we know the inverse function. F inverse of x, doing the relabeling, is equal to x squared minus 25 divided by 5. And the domain of this is the same as the range of f, is equal to 0 to positive infinity. Now let's try a cube root problem. Again, we want to know what is the inverse of this function. Cube root 3 minus x plus 4. Let's draw a quick sketch. This is a translation of the cube root. Let's see. We take a cube root problem. I know the cube root has a graph that looks something like this. And then we shift that over to the right by 3 units and then up by 4 units. So this point would be shifted over here. Now it'll look something like this. Just a quick sketch here to give us the idea. This is our graph of f. And notice the in behavior here. It goes from positive infinity to minus infinity to positive infinity. And so the domain of f will be the same as the domain of f inverse will be the same as the range of f, which is from minus infinity to positive infinity. Now let's find our inverse function. Set y equal to the cube root of 3 minus x plus 4. Now we want to solve for x, so let's subtract 4 first. Cube root of 3 minus x. Now let's cube both sides. Y minus 4 raised to the cube power will be equal to 3 minus x. Now, we need to solve for x. So let's add x to both sides and then subtract by this term. That says that x is equal to 3 minus y minus 4 quantity cubed. Now we have the inverse function, that is f inverse of x is equal to 3 minus y minus 4 quantity cubed, and has a domain minus infinity to positive infinity. Next, let's try a rational function. Let's first draw our picture here. This function has one x-intercept at 0. There's one vertical asymptote at positive 1. This example will have a horizontal asymptote in behavior at -1, equal degree up top and bottom. Oh, at -8 here actually. The ratio of the degree of the leading coefficients of 8 is 8 over -1, which is -8. And so the tail of the graph will be down here in both directions. There's only this one 0 So what must the function look like? We already have the x and the y-intercept. Has to cross here. It lives down here on the left side, and so this function will have to go up over here. There are no x-intercepts over here, and so the function must come from minus infinity over here over to here. So let's see, what is the domain of this function? No, what is the range of this function? Sorry. Here, we have this horizontal asymptote. Does this function ever attain the height 8? Let's see. Does this function cross this horizontal asymptote is the question here. I need to know the range so I know the domain of f inverse. I want to know, does it ever cross this height of minus 8? So let's set our function equal to minus 8. Is this ever true? Well, if this is true, let's multiply both sides by 1 minus x. Then 8x is equal to minus 8 times 1 minus x. So then 8x is equal to minus 8 plus 8x. Now let's subtract 8x from both sides. Oh, that's not true. So that's not true. That's not true, and this one's not true. Now I know what the range is. The range must be every number except this horizontal asymptote. Rational functions can cross horizontal asymptotes sometimes, but this one does not. So our range for this function is from minus infinity up to minus 8, not including it, unioned together with minus 8 up to positive infinity. Now let's find our inverse function. It's the same algebra as we've already done here. We set y equal to 8x divided by 1 minus x, and now we try to solve for x. Multiply both sides by 1 minus x. Y times 1 minus x is equal to 8x. Now we distribute here. Now let's collect every x term on the right-hand side. Oh, let me clean that up. Now we have x here and x here, so the right-hand side we can factor as x times y plus 8. Now we'll divide by y plus 8. That says that x is equal to y divided by y plus 8. Now we have our inverse function. Doing a relabeling, f inverse of x is equal to x divided by x plus 8. And it has a domain, which is the same as the range of f, that is minus infinity up to minus 8, together with minus 8 up to positive infinity. Let's try one more example here with a rational function. Let's again first draw a picture here and determine what is the range of f. This example has a 0 here, and it will have a vertical asymptote at 1 divided by 8, vertical asymptote here. The end behavior will be at positive 5 over 8. Same degree on top and bottom. The ratio of the leading coefficients is 5 divided by 8. Now, function must go from this end behavior through this root and go down here at this vertical asymptote. And so on the other side, since there are no other roots, the function must connect over to here. Now our question again, does this function actually cross this vertical asymptote? Let's test and see if that's ever true. Is 5x over 8x minus 1 ever equal to 5 over 8? Doesn't look like this one will be true either. So if it is, 5x will be equal to 5 divided by 8 times 8x minus 1. Multiply both sides by 8. That'll give us 40x is equal to 5 times 8x minus 1, which is 40x minus 1. Now subtract 40x from both sides. 0 is not equal to minus 1, so none of these are true. And so now we know what the range of f is. It's from minus infinity up to positive 5 over 8 unioned with 5 over 8 to positive infinity. Now we can find our inverse function. Set y equal to 5x over 8x minus 1. Multiply both sides by 8x minus 1. That's equal to 5x. Now distribute 8xy minus y will be equal to 5x. Collect every term with the x on it on one side. 8xy minus 5x is equal to y. Oof, let's clean that up. Now there's an x here and an x here. So x times 8y minus 5 is equal to y. And thus x is equal to y divided by 8y minus 5. So now we know the inverse function. F inverse of x, relabeling, is equal to x over 8x minus 5, and the domain, same as the range of f, minus infinity up to 5 over 8, union with 5 over 8 to positive infinity. Now let's consider some examples where we're given the graph of a function and our goal is to graph the inverse of f. Remember that if we have a function f and it's an ordered pair x comma y, then the inverse function is determined by the reverse ordered pair. So we're going to apply this idea in order to draw this graph. We're effectively going to flip this graph over the line y is equal to x. We're going to flip this graph over this line. And so let's label some of these ordered pairs. Let's label the ordered pairs corresponding to each of these points, wherever this function makes a turn and where it starts and stops. So this is the ordered pair minus 5 comma minus 3. This one is minus 2 comma 3, here 3 comma 6, and here 8 comma 7. So then our new ordered pairs, let's write our list over here. We just flip the order of these. Minus 3 comma minus 5, 3 comma minus 2, 6 comma 3, 7 comma 8. Now this is the list of ordered pairs corresponding to the inverse function of this function. Let's plot each of them. First, minus 3, minus 5, 3 comma 2, 6, 3, and 7, 8. Six, 3. Let's check each of these here. Minus 5, minus 3, minus 2, positive 3, 3, positive 6, and 8, comma 7. So then each of those we reversed. Minus 3, minus 5, 3, minus 2, 6, 3, and 7, 8. Let's try to draw a little bit better picture here. So if we draw it correctly, then we should really be flipping this graph over this straight line of slope 1, and so it should be a symmetric image about that line. Thinking of something like butterflies' wings. So let's plot these ordered pairs here. -3, -5, 3, 2, 3, -2. Come on. 3, -2, 6, 3, 7, 8. Now we can draw the straight line connecting each of those points. And now we have a sketch of our inverse function given this graph. Let's try another example. Here we're given this function, and so let's write down each of these 3 ordered pairs. This one's -7, -4. Here we have 3, -3, and here 5, 3. So our ordered pairs corresponding to the inverse will be -4, -7, -3, 3, and 3, 5. Let's put each of those on the graph. -4, -7, that lives down here, -3, +3, and then 3, 5. Now we can draw the straight line connecting each of those points, and we have our sketch of F inverse. Now let's try a word problem involving these inverse functions. Here we're given a function. Here the t and the h have a certain meaning. The input is h, which is a height. It's a distance measuring a height above the planet's surface. And then the output, T, gives us the temperature in the atmosphere of that height. Now what we want is to write down what will be the input and the output of the inverse function T inverse. Remember, we take the domain, T goes forward, input here was height, T takes the domain to the range value here are the temperature. And so the inverse function, it will eat a temperature and it will spit out the corresponding height. The input has to be a temperature and the output has to be a height. So let's see which of these statements describes that. Take x to be the output of the function t. Which statement best describes T inverse of x? So x is the output of T. X must be a temperature. And so T inverse of x must be a height above the surface of the planet. So T inverse must be the height above the surface when the temperature is x degrees Celsius. Now let's actually write down what is our inverse function. Here we have this nice straight line. And so our inverse function will be determined by solving for y given y is equal to 30.5 minus 2.5h. So we'll first subtract by 30.5, then we'll divide by minus 2.5. That will be equal to h. And so our inverse function, that's equivalent to x minus 30.5 divided by minus 2.5. And so for the second part, we just need to do a calculation given this inverse function. We just take this expression and plug in 15 minus 30.5 divided by minus 2.5. And so I'll let you do that calculation. Let's try one more example here where we interpret the meaning of the inverse function given this physical situation. Here, we have a function p whose input is in grams of vitamins. For p, the input in grams of vitamins, the output is the price. So now for p inverse, we flip the direction. Input will be price. The output will be in grams of vitamins. So which of these statements matches this? If X is the output of P, if X is a price, then what is the interpretation of P inverse of X? It must be the amount in grams of vitamins given that we started with a certain price. Now let's find our inverse function, P inverse. If y is equal to 0.4n plus 6.6, then y minus 6.6 is equal to 0.4n, and so y minus 6.6 over 0.4 is equal to n. Thus, the inverse function is determined as x minus 6.6 over 4.4. And then P inverse of 8.8 will be 8.8 minus 6.6 divided by 0.4, which is 2.2 over 0.4. And I'll let you finish this calculation.